infinite cylinder, so that means infinitely long, with radius r and a linear charge density, so charge over length lambda. The volume charge density rho is the position you're at times some constant divided by the radius of the cylinder. For part A, we want to draw a graph of density as a function of x, where the x-axis crosses the cylinder perpendicular to the cylinder axis. So let's draw a picture of what's happening here first. So here's our cylinder. Let's draw that guy. There's our cylinder. It says the x-axis crosses the cylinder perpendicular to the cylinder axis. The cylinder axis is this thing. Goes right down through the center. There's our cylinder axis. The x-axis goes up and down right through the center of that and perpendicular to it. There's our x-axis. We want to get some dimensions on there. This distance is the radius of the cylinder, and it has a length L. So we want to draw a graph of what is the density as a function of x. So from down here outside to touching the cylinder, inside the cylinder, through the center, and then outside the cylinder for a little bit. Let's think about what that density is in the different places. So let's first of all think from minus 2r to minus r, so from here to here. So if we have minus 2r less than x less than minus r, so outside the cylinder, on the bottom half, and 1 radius away. Right there, this density is only true when we're inside the cylinder, so when we're outside the cylinder, the density is 0. Okay, so next is when we're on the bottom half of the cylinder, so between negative r and 0, what is the density? Well, the density is our radial position. Radial position is how far are we along the x-axis. Got to be a little bit careful right here. If we just put in x, we're going to get a negative value for the density, but the volume charge density is not negative on the bottom and positive on top. It's positive on both the bottom and top. So for our coordinate, our radial coordinate, we'll say the absolute value of x. So that's what we'll put in for our r, our distance from the midpoint, times our constant, rho 0, divided by the radius of the cylinder. So that's what the density is when we're inside the cylinder on the lower half. When we're inside the cylinder on the bottom half, so x between 0 and r, our density is going to have the same expression, but we can drop the absolute value sign if we wish, because our x will be positive, which will give us a positive density. And then on the top, once we're outside, it's back to 0 again because we're outside. So for x between r and 2r, the density is 0. So now this is enough information to let us draw a sketch of the graph of rho versus x. So let's put rho on our vertical axis. Let's put x on the horizontal axis. Places we're interested in are minus 2r, r, 0, r, and 2r. So between minus 2r and r, our density is 0. Again, between r and plus 2r, density is 0. In between, so from negative r to 0, our density starts at a big value, rho naught, and it goes down to a small value of 0. So it jumps to here and it goes to here, and it decreases linearly as x gets closer to 0. Then once we're on the other side, it starts with x equals 0, so our density is 0. It goes as high as x equals r, so our density goes to rho naught, so it goes back up here on the other side. This graph is okay as is. If you wish, you can connect those dotted lines. And it's not a bad idea to show a scale here. So here the density is equal to rho naught. So there's our part A, our graph of rho versus x for this cylinder. Next we'll work on finding the constant rho naught.